In this video, we will look at the transistor, that basic but essential component of so many modern circuits and appliances. Many people have asked about transistors. They know what one looks like, but struggle to understand how they work. They are not alone. I struggled too all those years ago, and it was not until I went right back to the basics that I had that light bulb moment that told me, now I understand. Some of the questions that are asked have included, what is a transistor? What is it made of? How do transistors work? And can you show me a simple switching circuit such as nighttime lighting? So, let's get started and keep things simple and basic. First of all, what is a transistor? Transistors come in many shapes and sizes, and most of us will have seen these transistors in the course of our work, even if we've not understood what they are or what they do. Some transistors are enclosed inside tin cases, others come in the familiar black resin packages, and yet more with moulded on heat sinks. Transistors are called semi-conductors. Depending on the control voltage that is applied to it, sometimes it will conduct and allow current to pass through. At other times, the flow of current is stopped. In other words, it is switchable. With the correct voltages on the appropriate terminals, we can have a small input current controlling a larger output current. When were transistors invented? How long have they been around? For many electricians and electronics engineers, transistors have been an essential part of life since they were born. But there will be many who remember the humble vacuum tube technology, or valves, waiting for the valve heaters to begin to glow, and the subsequent heat output, and televisions that could warm a room all on their own. Transistors were made a viable electronic device in the years just after the Second World War, so they've been around now for almost 80 years. Credit for inventing the transistor goes to William Shockley, John Bardeen and Walter Brattain. These three researchers worked at Bell Telephone Laboratories, and in 1947 they developed the first very basic point-contact transistor. In 1956 they were jointly awarded the Nobel Prize in Physics for their pioneering work. The transistor has gradually replaced the much larger vacuum tubes, almost eliminating their use entirely within 3 decades. Over the last half century or so, the transistor has been miniaturized to the point where thousands of transistors can now be manufactured on a piece of silicon about the size of a match head. Without the transistor, the information technology age, as we know it, would never have happened. There are 2 types of transistor, the Npn transistor and the Pnp. Notice the direction of the arrows on the emitter of the 2 drawings on the left. An Npn transistor has an emitter arrow that points out of the circle, while a Pnp transistor has the arrow pointing inwards. They both perform in a similar way, but how they work and how to connect them is oh so very different, and they are not interchangeable. The Pnp transistor, made from the element germanium, was common for many years as transistor technology developed, but their use and popularity has been overtaken by the silicon-based Npn transistor. Today, most transistors and integrated circuits are manufactured using silicon as the principal element. And, believe it or not, silicon is the second most abundant element on the planet. Perhaps a good thing when you look at just how much we depend on electronics today. And it is these Npn transistors that we will show you in the rest of this video. To begin with, think of the transistor as a simple switch. With the contacts open, the switch is off. no current can flow through the switch. When the switch closes, current can flow through the switch and do useful work such as illuminating an LED, making your mobile phone ring, or enabling the sat-nav in your car. What happens is, a small current between the base and emitter terminals will cause a large current to flow between the collector and emitter, easily 100 times greater. And it is this greater current that can be made to do useful work for us. For example, operating a relay that turns on a lamp, as we will see in the example at the end. The difference between the current that is input at the base and the much greater current that flows through the collector is known as the gain of the transistor, and this is often referred to as the HFE, or beta, of the transistor. Silicon transistors are made from very pure silicon with the chemical symbol Si. The silicon is doped or infused with other elements such as arsenic, boron, gallium and phosphorus to make either an N-type region with extra electrons or a P-type region with a depletion of electrons, or, to put it another way, an abundance of holes. The sketch of an Npn transistor shows the heavily electron-doped N-type region of the collector and the emitter, separated by the hole-rich region of the base. The next question is, where does the silicon come from? Silicon is made by processing sand, but it must be a particular type of sand, not just a bucket or two collected off Blackpool Beach. To achieve the required quality and purity, the silicon is manufactured using very sophisticated and highly controlled processes in super clean environments. The best sand in the world that is used to make silicon for transistors and integrated circuits comes from a mine just west of Glasgow in Scotland. Because of the NP and PN junctions in an NPN transistor, a positive voltage on the collector and a negative or zero potential on the emitter, we have a reverse biased NP collector half and a forward biased PN emitter half. This means that it is difficult for any current to flow through the transistor from the collector without a little help. However, help is at hand, as it is easy for the current to flow from the base to the emitter, and once the base emitter current begins to flow, the collector current will flow too. When we talk of forward and reverse biasing, think of the common diode. This was covered in detail in a previous Learn Electrics video, and we will leave a link to that video in the descriptions for this video. A positive voltage arriving at the forward biased P side of a diode will pass through, as shown in the top drawing. The pulsed input appears as a pulsed output. Turn the diode around, and now we have a reverse biased device with a positive pulse voltage meeting the N side of the diode. The signal cannot pass through, and we have no output, 0 volts. If we want to switch the transistor on, we must supply a switching voltage to the base terminal. This switching voltage needs to be 0.7 volts or greater than the voltage on the emitter, which most often sits at 0 volts. Achieve this and the transistor will turn on. This flow of current from base to emitter causes the reverse biased collector base junction to break down, and this allows a much larger current to flow from the plus volts to the 0 volts. How much greater depends very much on how the transistor has been designed. It depends on the HFE or beta of the transistor, the gain factor. No voltage at the base, the transistor is effectively off. No current flow from the base to emitter means no current flow from the collector to the emitter. Going back to our open and closed switch analogy, this is what is happening. If there is no voltage at the base, the switch remains open and prevents any current flow from the collector. If we now provide a voltage at the base, the switch will close and the current can now flow through the switch. If we make a simple nightlight circuit, we can see this on and off change of state happening. We want a lamp to illuminate the driveway when it goes dark and to turn off when daylight returns, and it must do this automatically. This is our basic circuit. During daylight hours, there is insufficient voltage at the transistor base to turn the transistor on. The relay contacts remain open and the lamp is off. This is because of the light-dependent resistor, or LDR, that is part of the lamp assembly. During daylight hours, the light-dependent resistor has a low resistance, which results in a low voltage on the transistor base from the A and B potential divider. The sunlight causes the LDR to have a low resistance, and so the voltage drop that is across B, the LDR, is a lot less than the voltage drop across A. The voltage at the base will be close to 0 volts. You will notice a diode installed across the relay coil. This is called a flywheel diode, and it suppresses or limits any back EMF or spikes that are produced when the relay switches states. It prevents electrical damage. With the relay switch open, 230 volts cannot pass through, so no current to illuminate the driveway lamp. The sun sets and the driveway becomes dark. During darkness, the resistance of the light-dependent resistor will increase dramatically and the voltage at the base will rise as the potential at the A and B junction changes. Less voltage is dropped across resistor A and more across resistor B, eventually reaching that important 0.7 volts. The transistor turns on and current flows through the transistor and through the relay coil. The relay pulls in and the contacts close, allowing 230 volts to illuminate the driveway lamp. During nighttime hours, the LDR will have a high resistance, resulting in a higher voltage on the transistor base. Transistors act as switches controlled by the input voltage on their base terminal. A transistor is a semi-conductor device. When switched off, it will not conduct electrical current, but given the right level of voltage on the base, it will begin to conduct. A typical general-purpose transistor might produce a collector current 100 times greater than the base current. Manufacturers' data sheets will give this information. We've looked here at a transistor acting as a simple on and off switch, but transistors can also be used as amplifiers. They can be only partly on, or more, to a greater or lesser extent, by controlling the input current at the base. That is to say, that if a varying signal is applied to the base, the collector current will follow the varying input signal and amplify it according to its HFE or beta value. Think of a radio broadcast. A fairly weak signal arrives over the airwaves and several stages of transistors will amplify the signal to give music or talking out of the speakers. Transistors come in many shapes, styles and function, from small signal transistors to fairly chunky power transistors that require heat sinks. Transistors are available as NPN silicon types, as in this video, and also as the lesser used PNP germanium types. Thank you for watching. I hope that you found this video useful and informative. Please subscribe to our channel to get access to all of our videos, and remember to click on notify to be sure of not missing our next video. And don't forget, you can also type in Learn Electrics into the YouTube search bar to go directly to our channel at any time from any computer or smart device. We are always adding new videos to our channel, so don't miss the next one. And once again, thank you for watching, and we hope to see you again very soon.